Good morning, vector calculus, our second class. So the syllabus topic for today is vectors in 3 dimensions, and I had already uploaded a little video lecture onto YouTube. And I'm happy to answer any questions you might have about vectors in 2 dimensions, vectors in 3 dimensions.
Professor,
Yes, sir.
what happened on Monday? The line cut off after 30 minutes. After 40 minutes, I think we can't see you anymore. You ended.
So I post the lectures in advance on YouTube, and these Zoom sessions are really problem sessions to answer questions. And we start at 11 o'clock.
Okay.
And if we finish, whenever we finish, we end. So there's no reason. I don't stay on Zoom after the class is ended.
Yeah, but my question is that the class ended like, it's not 1 hour, I think it's 40 minutes, that's it?
No. So the this time slot is from 11 o'clock to 12:40.
Yes.
It's an hour and 40 minutes.
Okay.
But in addition, I'm making lectures in advance and posting them online. So I stay online in these Zoom sessions, maybe from 11 to 12:40, but if we're done at 12 o'clock, then we end at 12 o'clock. There's no reason to continue if there are no questions from you or other students.
Okay.
All right. That's
So,
one reason why I posted the lectures in advance. It makes it easier to see the material. I also review all the material in this class, but it doesn't take the full 100 minutes. So if you don't log on at 11, if you log into the class at 12 o'clock, it may be the class is ended. There's nothing to log into.
So Monday schedule and Wednesday, is it going to be for review session or what?
The Monday and Wednesday classes, I review the material that I've already put online, I hope, and I answer questions.
Okay.
Go over homework problems. Whatever any student has to ask, I'm happy to try to answer.
Thank you.
Okay. So in fact, since the book is online, let me just turn to the book and I'll talk about the book a little bit, and then I'll work some problems on paper. So let me see what happens when I share the screen. And so you should see the textbook right now. And we're talking about section 13.2, which is vectors in 3 dimensions. And as I pointed out on Monday, if you draw, you can't draw 3 dimensions on a 2-dimensional surface. So you can sort of try to sketch the idea of what a 3-dimensional space looks like when you're using a 2-dimensional piece of paper. And typically you draw it the way you see the pictures here in 13.25. You have an x-axis and a y-axis, and you can determine, or you can decide arbitrarily where they intersect is the origin. You think of this angle as a right angle. Obviously, it's not a right angle, it's an obtuse angle the way it's drawn, but you think of this as a right angle, and you can choose either branch of the x-axis or the y-axis to be positive. So you pick a positive branch. Let's say this is the positive x direction. This is the positive y direction. And then perpendicular to the xy plane, you draw the z-axis. Again, you're drawing in 2 dimensions, so you have to use your imagination a little bit to understand what's going on. And the question is, in the z-axis, it goes up and down. and which direction is positive and which direction is negative. So the convention is to always use what is called the right hand rule. So if you take your right hand and you place it around the left axis, around the Z axis, and you do it so that when you turn your fingers from the X axis to the Y axis, the direction your thumb is pointing is the positive Z direction. And you can check if you take your left hand and you put your fingers around the Z axis, and you turn with your fingers the X into the Y, your thumb will be pointed in the opposite direction. So there's a complete difference between the positive and negative Z axes, depending on whether you use a right-hand coordinate system or a left-handed coordinate system. And in math and physics and generally, one always uses the right-handed system. And just as the X-Y axes divide the plane into 4 quadrants, the XYZ axis divides 3-dimensional space into 8 octants. And it's hard to draw things, but here is a picture, and if you spend a little bit of time thinking about it, you get to see and you get a feeling for what the 8 different octants are. Okay, any questions about that? And you plot coordinates in 3-dimensional space exactly the way you plot coordinates in 2-dimensional space. So if you take the point 3, 4, 5, this corresponds to a unique point in 3-dimensional space, and you understand it as follows. 3 means you go 3 units in the along the x-axis. 4 means 4 units along the y-axis. 5, the third coordinate is 5 units up on the z-axis. So 3, 4, 5, you end up a point right here in 3-dimensional space. Or here is with coordinates, 3 in the x direction, 4 in the y direction, 5 in the z direction, you have this point. And again, you just have to get used to thinking about 3 coordinates instead of what you're typically used to doing, which is dealing with just 2 coordinates. So in freshman calculus and beginning calculus, you're only studying functions in the plane. You only have x and y axes. Everything is 2-dimensional, and that's what you're familiar with. If you fix one coordinate, like x equal 2, and you can ask, what are all the points in 3-dimensional space for which x is equal to 2? And that's a plane. It's a 2-dimensional plane in 3-dimensional space parallel to the YZ plane. If you fix an x coordinate, you get a plane parallel to the YZ plane. If you fix a y coordinate, you get a plane parallel to the XZ plane. And if you fix the z coordinate, you get a plane parallel to the XY plane. So these are the simplest planes you have in 3 space. There are other planes. You can have planes that make an angle with respect to the axes. But these are the coordinate planes. And these are really basic things to understand. Okay. Any questions about that? So just as there's a formula for the distance between 2 points in the plane, right? So again, this is all supposed to be very familiar from Calc 1 and Calc 2. If you take the point x1, y1 in the plane and the point x2, y2 in the plane, the distance between them is given by this formula. It's the square root of the sums of the squares of the differences of the coordinates. It's just the Pythagorean theorem. It's no more than that. And there's an analogous formula for the distance between 2 points in 3-dimensional space. So if you have a point with coordinates x2, y2, and this is a typo, Well, it's not a typo, but it's strange. If you have points with coordinates x1, y1, z1, and x2, y2, z2, this is the formula for the distance between the 2 points in three-dimensional space. And you can also derive this from the Pythagorean theorem. That's what this drawing is explaining. And again, it's the square root of the sum of the squares of differences of coordinates. Right? That's the distance between 2 points in three-dimensional space. And this is a fundamental formula that you have to know. The midpoint between them. So if you have the points P and Q, and you draw this line between them, this formula, the square root formula, gives us the length of the line. If you want the midpoint of the line, you simply take the average of the x, y, and z coordinates. That's exactly this. Okay.
Professor, can you scroll up a little bit so I can look at the second formula? Yeah, right there.
Okay.
Thank you.
Again, if you are logged, if you log into my lab, you have the book and you can just have it on your screen all the time, but there it is. Yes, we're happy to do that. Okay, can I go on?
Yeah, Professor.
Yes, sir.
So the distance formula is used for S, Y, and Z space, right?
Yes.
Okay. Thank you.
Okay. So a sphere, by definition, is the three-dimensional analog of a circle. So in the plane, the circle is the set of all points of fixed distance from the center. And in 3 space, a sphere is also the set of all points of fixed distance from the center. The distance is the radius of the sphere, just as it's the radius of the circle. So if we want the sphere where the center is at a point ABC and the radius is R, so ABC is the center, all the points of distance R from the center form the sphere. And the inside of the sphere and the sphere itself is called a ball. So a ball is the three-dimensional analog of a two-dimensional disk. So in the plane, the circle is the points a fixed distance from the center. The disk is all the points a distance less than or equal to that fixed distance R from the center. And in the same way, in three-dimensional space, the sphere is all points a fixed distance R from the center. And the ball is everything inside the sphere, on the sphere and inside the sphere. And there's a simple equation for the sphere whose center is at A, B, and C, and whose radius is R. It's all the points where the distance from X, Y, Z to A, B, C is R. And if you square the distance formula, you get this sum of squares. So that's the formula for the distance of so point X, Y, Z, which is distance R from A, B, C, will satisfy this equation. And any point that satisfies this equation is also on the sphere. Now, just as in the case of a circle, a diameter of a sphere is a line that goes through the center of the sphere from one point on the sphere to the opposite point on the sphere. So if you have 2 points P and Q, and they're the endpoints of a diameter, then the center of the sphere is going to be the midpoint of the line from P to Q. So if P has coordinates 1, -2, 5, and Q has coordinates 3, 4, -6, the center is going to be the midpoint, which means you take the average of the X, Y, and Z coordinates. So the average of 1 and 3 is 2. The average of -2 and 4 is 1. The average of 5 and -6 is -0.5. So the sphere that we're considering has the 0.21 minus 0.5 as its center. And this will be the equation of the sphere. The distance from P to Q is the square root of 161. That means that's twice the radius. So this divided by 2 is the radius, and then the square of the radius will be then 161/4.
Professor,
Yes, sir.
on the solution for the center for the sphere, where do you get over 2? You have 1 plus 3/2. Where do you get the 2?
Where do I get this 2? This 2?
No, the one on the solution.
I'm sorry, there's a little bit of static on my
Where,
line.
where do you have 1 plus 3/2, comma, minus 2 plus 4?
Oh, so
Where do you
here's
get?
the point P and here's the point Q.
Yes.
They're part of a diameter. So that's the line through the center of the sphere. And I want to find the midpoint of that line. That will be the center of the sphere.
Okay.
So the way I find the midpoint between 2 points in 3 space is I average the coordinates. So here the x coordinate is 1, here the x coordinate is 3. The average is 1 plus 3/2, which is 2.
Okay. I got it.
That's where that comes from.
Thank you.
Okay. Other questions? So we have the same vector operations in space as we have in the plane. So if you take a scalar c, a vector u and a vector v, you add the vectors by adding coordinates. You subtract the vectors by subtracting coordinates, and you multiply a vector by a scalar, by a number, by multiplying each coordinate by the scalar. So if I have the vectors 2, -4, 1, and 3, 0, 1, a half u, what does that mean? That means scalar multiply the vector u by a half. So you multiply each coordinate by a half, you'll get 1 minus 2, a half. That's what you see here. If you want to compute the vector minus 2v, you multiply the coordinates of v by -2. You get -6, 0, plus 2. And u plus 2v, you multiply v by 2 and add u. So for example, when you multiply v by 2, the first coordinate will be 6. When you add the first coordinate of u, which is 2, you'll get 8. So when you look at u plus 2v, here is 8 as its first coordinate. And you can draw this somehow by using the parallelogram rule. They try to draw pictures of these things, but it's really very hard. So here is the vector u. Here is the vector v. 2 vectors, 2 lines determine a plane. So in that plane, which is a skew plane, it's not parallel to any of the coordinate planes, you have u, v, here's the parallelogram they form, and the diagonal is u plus 2v. All right, any questions about this? So the length of a vector is just the distance from the vector to the origin. It's also called the magnitude of the vector. And if you have the vector from P to Q, these are its coordinates in terms of the coordinates of P and the coordinates of Q. The length of the vector is just the distance from P to Q, so it's exactly the same as the distance formula. There's no difference at all. So there are three basic, what are called unit vectors in space. A unit vector is a vector whose magnitude or length is 1. In the plane, we had a unit vector in the positive x direction and a unit vector in the positive y direction. These were called I and j. And in space, we have those two vectors, and in addition, a third vector, k, which is a unit vector in the positive z direction. So here we have x, y, and z, our coordinate axes. The vector I is a unit vector in the x direction. The vector j is a unit vector in the y direction. And the vector k is a unit vector in the z direction. X, Y, Z. And then you have a simple way to write every vector as a linear combination, scalar multiples of these fundamental coordinate unit vectors. So, because if you take a vector v, where the coordinates are v1, v2, v3. So if you take v1 times I, that's v1 times the vector 1, 0, 0. And v2 times j is v2 times the vector 0, 1, 0. v3j is v3 times the vector 0, 0, 1. So when you do your scalar multiplication, this is v1, 0, 0. This is 0, v2, 0, and this is 0, 0, v3. And when you add, you get v1, v2, v3. So we have this way to represent every vector in terms of the unit vectors I, j, and k. And if you study, for example, physics, you use this form of representation all the time. It's very standard. So here's an example, and maybe you should try to work this out yourself right now with a piece of paper and then check the solution. We have a vector P with coordinates 5, 3, 1, and a vector Q with coordinates -7, Q1. So there is a vector from P to Q. So calculate its coordinates and write them in terms of the unit vectors I, j, and k. And then find the magnitude of the vector from P to Q, or the length of the vector. And then find a vector of, it says of magnitude 10 in the direction of P and Q. So let's just make sure we understand what all the different words mean. If you go from P to Q, the first coordinate will be -7 plus 5. Sorry, -7 minus 5. You take the difference of the coordinates. That's -12. The second coordinate will be 8 minus 3. That's 5. The third coordinate will be 1 minus 1. That's 0. So the vector from P to Q is -12, 5, 0. And if you write this in terms of I, j, and k, it's -12i plus 5j plus 0k. And 0 times the vector is just the 0 vector. And there's no reason to write it. You could write 0 times k here, but it's just 0. There's no reason to write it. And so the length of this vector is the square root of the sums of the squares of the coordinates. And 12 squared plus 5 squared is 169, and the square root of 169 is 13. So if you want a unit vector, a vector of length 1, in the direction of the vector PQ, you take PQ divided by its length, the PQ divided by 13. So 1/13 times this vector. So this is a unit vector, a vector of length 1, that points in the direction of PQ. And if you want a vector of length 10 pointing in that direction, you just multiply this unit vector by 10. So you get 10/13 times minus 1250.
Professor.
Yes,
And number B. So find the magnitude means like you have to find the length, right?
yeah, magnitude and length are the same thing.
Okay. Magnitude B. Okay. Thank you.
Mhm. Wow. So here's an example of the use of vectors. So you see the picture in 13.42. So a plane is flying horizontally. That means it's not going up or down. It's just flying parallel to the surface of the earth. And it's flying due north at 300 miles an hour. So in calm air, here's the northward direction. The plane is flying north 300 miles an hour. Now, the way this coordinate system is set up, the x-coordinate, positive x-coordinate pointing east is here, and the y-coordinate is pointing in the positive direction towards the north. So the plane is flying with a velocity of 300 miles an hour in a certain direction, and it's in the direction of the unit vector j. That means it's flying parallel to the y-axis. There's no other component. But then suddenly there's a crosswind blowing southeast at 40 miles an hour. So what does southeast mean? Well, if north is the positive y-axis, south is the negative y-axis. And southeast means halfway between going south and going east. So you're still in the XY plane, but we are in the quadrant where X is positive and Y is negative. That's the fourth quadrant, the way you would usually draw this. And if the plane is hitting a crosswind that is going at 40 miles an hour southeast. So maybe I will switch to a piece of paper so I can draw this, and then we can try and see more clearly perhaps what this problem is describing. So let me go to my paper. So let me just, I'll switch directly to the paper in a moment. I just want to write down the data. So let's see. Stop share. Perfect. So this is in the text. Example 7. And this is the X direction, which is east. This is the Y direction, which is north. This is the Z direction, which is vertical, up and down. And initially, our plane is flying north at a speed of 300 miles an hour. And then we find a wind which is blowing southeast.
Roberto, can you move that a little bit?
Mhm.
Thank you.
At 40 miles per hour. And it's going downward with a force of, a force of 30 miles per hour. And we want to find the speed in the direction of the plane relative to the ground. Okay, so I just want to, okay. So what can we say about the wind? First of all, if the wind is blowing 40 miles an hour in the southwest, let me just draw it like this. So this is X, Y. This is north. This is east. That means this is south and this is west. So southeast is in this direction, right? Southeast. And this angle, these two angles are pi over 4 radians. And the wind, the force of the wind or the magnitude of the wind in the southeast direction is 40. So what are the X and Y components of this vector? What is this vector? So this is going to be 40 times the cosine of pi over 4. And this is going to be minus 40 times the cosine of pi over 4. Cosine of pi over 4 is 1 over root 2. So this is 20 root 2 and minus 20 root 2. So the wind, the vector that represents the wind blowing in the southeast direction has coordinates 20 square root of 2 minus 20 times the square root of 2. Or we could write this as 20 root 2i minus 20 root 2j. So let me just stop for a minute here, because this is a simple use of vectors, but like many things, it's only simple after you understand it well, and until you understand it, it can be very confusing, right? So if this is north, south, east, and west, the southeast direction is in the direction of a vector that makes an angle of pi over 4 with respect to the positive x and negative y axes. And a vector in that direction of length 40 will have coordinates 20 root 2i minus 20 root 2j, or you could also write this as 20 root 2 times I minus j. So that's the crosswind. That's the component of the crosswind that is blowing horizontally, right? But now there's also a downdraft. There is part of this wind which is blowing how fast? 30 miles an hour downwards. So as a vector, that's minus 30k. It's minus 30 in the k direction. So the wind vector is what? The wind vector is blowing in the same horizontal plane as the airplane, 20 root 2 I minus j, plus the downward thrust of the wind, which is minus 30k. So this is the wind. Meanwhile, the plane, you recall, the plane was flying north at 300 miles an hour. So the velocity of the airplane was 300 J. So this plane is flying 300 miles an hour. There is this horizontal component of the wind, 20 root 2 I minus J. Let me just call that W. And then there's the downward force of the wind. I'll call this D for downward. So the motion of the plane, the velocity vector of the plane is 300. That's what the plane is doing. Oh, let me just write it. So the velocity is the velocity of the plane plus the wind plus the downdraft. So that's 300K plus 20 root 2 I minus J plus the downdraft. What was the downdraft? Minus 30K. So the actual movement of the airplane relative to the ground is 20 root 2 I minus 20 root 2 J plus 300 minus 30 plus 270K. Oops, sorry. This is 300J. Let me do this right. Plane is going horizontal, 300J. So this is 20 root 2 I plus 300 minus 20 root 2 J minus 30K. So this is the velocity of the plane, which is a combination, it's the sum of the plane's velocity vector plus the wind vector plus the downdraft vector. Okay, any questions about that?
Professor, you said plus D vector or D down?
Yeah, so the D is the downward draft
Okay,
of the wind.
Okay, downward, thank you.
Yes, that's minus 30.
Can we have upward or only downward has to be?
Well, the wind is either blowing up or down. It's not doing both at the same time.
Okay.
You have a wind vector. There's a component in each of the X, Y, and Z directions. If the component in the Z direction is negative, it means the wind is blowing down. If the component in the Z direction is positive, it means you have an updraft and the wind is blowing up. Okay, well, let me do a couple of problems that are in the exercises at the end of this section, just for fun. So this is number 45, if you look at the book. If I take the vector P with coordinates 1, 5, and 0, and the vector Q with coordinates 3, 11, and 2, I want to find the vector from P to Q, the length or magnitude of the vector from P to Q.
Professor, we can't see that.
Sorry.
Yeah,
And
thank
2 unit vectors in the same direction as P and Q. So here's P, here's Q, and I want this vector PQ. So the vector from P to Q is the difference of the coordinates of P and Q. 3 minus 1, 11 minus 5, 2 minus 0. So that's the vector 2, 6, 2. That's the vector PQ. The length of the vector is the square root of the sum of the squares of the coordinates. So this is 4 plus 36 plus 4. That's the square root of 44, or 2 times the square root of 11. That's the length of P and Q. Now, you can get one unit vector in the direction of PQ by taking the vector PQ and dividing by its length. So that's 1 over the length, 2 times the square root of 11, times the vector 2, 6, 2. So if you scalar multiply this vector by this scalar, you get 1 over root 11, 3 over root 11, 1 over root 11. So this is a unit vector. You can check. What is the length of this vector u? You take the square root of the sum of the squares of the coordinates. You square 1 over root 11, you get 1 over 11. Square 3 over root 11, you get 9 over 11. Square 1 over root 11, you get 1 over root 11. So what I have is the square root of 11 over 11, or 1. So this is a unit vector. And it's parallel to the vector PQ. It's the scalar multiple. And another unit vector parallel to PQ, well, there really can only be one, namely the unit vector, but points in the opposite direction. So minus u, which would be the vector whose coordinates are minus 1 over root 11, minus 3 over root 11, 1 minus 1 over root 11. So it's like, here we have u, this is 0. And this is v, which is minus u. And these are both unit vectors parallel or in the same direction, or parallel to PQ.
Professor,
Yes.
how do you get the 1 over 11 plus 1 over 11 plus 1 over 11 on the units?
So in general, if you have any vector v, which is not the 0 vector, if you take 1 over the length of the vector times v, this is always a unit vector. The length of this will be 1. So in our case, my vector is PQ. PQ has coordinates 2, 6, 2. The length of PQ is the square root of the sum of the squares of the coordinates. That's 44, or 2 times the square root of 11. That's the length of PQ. So to get a unit vector in the direction of PQ, I take the vector PQ and I scalar multiply it by the number 1 over the length of PQ. So the length of PQ is 2 root 11. So this is 1 over 2 root 11 times the vector 2, 6, 2. And when you scalar multiply, you multiply each coordinate by the scalar. I get 2 over 2 root 11, 6 over 2 root 11, 2 over 2 root 11, and the 2's cancel. So I get 1 over root 11, 3 over root 11, 1 over root 11. So if you were asking where these numbers come from, this is where they come from.
Yeah, but I'm also asking, how do you ended up getting also the 1 over 11 plus 1, what plus 9 over 11 plus 1 over 11?
Well, I'm just confirming that the length of this vector. So, so U is this vector. 1 over root 11, 3 over root 11, 1 over root 11. What is the length of this vector? It's the square root of the sum of the squares of the coordinates. I square 1 over root 11, I get 1 over 11. I square 3 over root 11, I get 9 over 11. I square 1 over root 11, I get 1 over root 11. I add, I have 11 over 11 or 1. So this is just a check that this really is a vector of magnitude 1.
Oh, okay. Okay. Thank you.
Right?
Mhm.
Any other question?
So
Sorry?
the unit of vector must equal to 1, right?
The unit vector is what?
Does it mean that it has to equal to 1?
Well, the definition of a unit vector is a vector whose magnitude is 1.
Okay.
That's
All
the
right.
definition.
Thank you.
Okay. Let's look at some more of these problems because they're useful just to get some practice dealing with points in three-dimensional space. So some of these involve drawing pictures, which is hard to do. So let me make an effort to do one just as an example. So this is problem number, these are problems 15 to 20. It says, sketch some planes in the window from 0 to 5 in the X, Y, and Z directions. So,
Professor, you can put the paper down a little bit.
sorry?
Oh, you can put the paper down a little bit.
Yeah, that's all it is. So if you think of this as the origin, this is the point 5, 0, 0. This is 0, 5, 0. This is 0, 0, 5. These are the coordinate axes. And then I use those to make a cube, a box. So this is the 0, 5 times 0 to 5 times 0 to 5, what the book calls the window or a box. And we want to sketch the plane x equal 2. So along the x-axis, 1, 2, 3, 4, 5, the plane x equal 2 is the plane parallel to the YZ plane going through the point on the point x equal 2 on the 2 axis. That's the plane x equal 2. Right? So it's a plane parallel to the YZ axis. Suppose I want to sketch the plane that passes through the points 2, 0, 0, 0, 3, 0, and 0, 0, 4. So this is the point 2, 0, 0. This is the point 0, 3, 0 on the y-axis. This would be the point 0, 0, 4 on the z-axis. So I have these 3 points on the axes. And what does a plane that passes through them look like? Well, let me just draw the lines connecting these 3 points. Right? That's a triangle. And a triangle is part of a plane, and I just extend that triangle. So the plane passing through these 2 points is just the plane defined or determined by this triangle. So this plane is not parallel to any of the coordinate axes. This plane cuts each of the coordinate axes somewhere at the points 2, 3, and 4, respectively. Okay. All right, any questions about that? And again, this is just a lot of playing around with pencil and paper to try and figure out what's going on. Let's look at one more example here. Suppose I want to sketch the plane through the point 2, 4, 2. And parallel to the XY plane. So this is the XY plane. This is the Z-axis. Where is the point 2, 4, 2? That means you go 2 units in the X direction, 4 units in the Y direction, and then up 2 units in the Z direction. So this is the point 2, 4, 2. And the plane parallel to the XY plane, well, if you're parallel to the XY plane, it means you have a fixed Z coordinate and X and Y can vary. So this plane through this point parallel to the XZ plane has a very simple equation. It is all points with Z equal to 2. That means all points which are 2 units above the XY plane. So 2, 4, 2 is 2 units above the XY plane. Z is equal to 2. And this is a plane parallel to the XY plane. So this is the solution to that geometrical problem. So I'm gonna pause for a minute because you have to really try and do this yourself with pencil and paper and get some feeling for what is going on. Any questions about this? Let's look at a more basic problem, perhaps. I'm sorry, is there a question?
Yeah, I had a question. When you go back to, how would you sketch it, like for the answer?
Well, you know, sketch it like that.
Short, okay.
I mean,
And that would be the answer, right?
yeah, yeah.
Professor, I know you said you were going to do the test on my math lab. So like, is there like, are there going to be questions where we're going to have to sketch in the lab or like,
I
we gonna-
doubt it very much.
okay, it's just something that we should know for vector calculus how to sketch. Right?
Correct. Yes,
Okay, thank you.
because otherwise you have to have some sort of feeling for what's going on. Like when you have functions in space, you have to have some idea like what their graphs would look like.
Okay.
Professor,
Yeah,
what time is problem session?
this is a problem session.
Oh, okay. All right.
I mean, once we get a little bit further into the course, I'll have additional problem sessions besides these Monday and Wednesday classes. Next week
Got
is funny because there's only one class, right? Because Monday's a holiday, so there's just class on Wednesday. But starting the following week, I'll also have some additional problem sessions.
Okay.
You know, maybe one on Friday in case you have some questions that you want to have answered before the weekend. All right. Okay, here's another typical type of problem. This is problem number 39. We have u is the vector 4 minus 3, 0, and v is the vector 0, 1, 1. So we want to compute the vector 3u plus 2v. And we want to compute the vector 4u minus v. And we want to compute the length of 3 plus uv. So how do we do that? Well, this is u and this is v. So 3u is 3 times 4 minus 3, 0. And 2v is 2 times 0, 1, 1. When you multiply this vector by 3, you get 12 minus 9, 0. When you multiply this vector by 2, you get 0, 2, 2. And when you add, you get 12 minus 7, 2, if I did my arithmetic correctly. So 3u plus 2v is this vector. 4u minus v, that's 4 times 4 minus 3, 0, minus 0, 1, 1. 4 times this is 16 minus 12, 0, minus 0, 1, 1. And when I subtract coordinates, I get 16 minus 13 minus 1. If I want the length of 3 plus UV, well, first I have to know what is the vector 3 plus UV, or U plus 3V. So U plus 3V is the vector U is 4 minus 3, 0. And 3 times the vector V is 0, 3, 3. And when I add them, I get 4, 0, 3. So the length of U plus 3V is the length of the vector 4, 0, 3. That's the square root of the sum of the squares of the coordinates, 4 squared plus 0 squared plus 3 squared. That's the square root of 25, or 5. So, all right. Again, these are all basic questions about right. Actually, this is good practice. I want to keep doing some more problems. This is problem number 67. It says, write a vector. Sorry. Write the vector V equals 2 minus 4, 4 as a product of its magnitude and the unit vector in the same direction. All right. So I'm going to write this as the product of its magnitude times the unit vector in the same direction. What is the magnitude of this vector V? So the length of V is the square root of the sum of the squares of the coordinates, 2 squared plus minus 4 squared plus 4 squared. This is 4 plus 16 plus 16. That's the square root of 36, which is 6. So this vector has length 6. A unit vector in the same direction as V, you just take 1 over the length of V, 1/6 times V. That's 1/6 times 2 minus 4, 4. So this is the vector 1/3 minus 2/3, 2/3. So this vector has length 1, and so the vector V is 6 times the vector times the unit vector, 1 over root 3 minus 2 over root 3, 2 over root 3. So here I've written the vector V as the product of its magnitude, which is 6, times the unit vector in the same direction. Right. Questions about that?
Yes, how do you get the unit vector of 1/6?
Well, no. So the way you get, if you have a vector and you want a unit vector in the same direction, you scale or multiply the vector by 1 over its length. So this vector V has length 6, right?
Mm-hmm.
So if I multiply V by 1 over 6, that gives me a unit vector in the same direction as V. Right? So U defined to be 1/6 times the vector V, that gives me this. This is a unit vector in the direction of V.
Professor, I have a question. Where did you get
Wait,
the
just one
square
second.
root of
So the
3?
person who just asked me a question, is that clear, or do I need to explain some more?
No, that's clear. Thank you.
Yeah, okay. Next.
Yeah, I was asking, where did you get the square root of 3? Where you got the, where you did the 1/6 times the
Oh, that's
vector
the
v?
typo. That's just 3.
Okay, okay. Oh, it's supposed to be 3s. Okay.
Yeah, that's the unit vector. 1/3 minus 2/3, 2/3. Yeah. Thank you. Okay, let's have another problem. Number 5, let's say. So, sorry, not number 5. This is going to be problem number 69. Find a vector of length 5 in the direction opposite. So not in the same direction, but in the opposite direction of the vector 3 minus 2 square root of 3. So here we have a certain vector, and I want to find a vector going in the opposite direction and whose length is 5. So let me just call this vector v for the moment. What is the length of v? So the length of this vector v is the square root of 3 squared plus minus 2 squared plus root 3 squared. That's the square root of 9 plus 4 plus 3, which is the square root of 16, which is 4. So this vector has length 4. If I take 1/4 times the vector v, which is the vector 1/4 times 3 minus 2 square root of 3, that vector has coordinates 3/4 minus root 2 over 4. Sorry, less than minus 2, 3 minus 2 root 3. Root 3 over 4. So this is a unit vector pointing in the same direction as v. But if I want a unit vector pointing in the opposite direction of v, I want to take minus this, so minus 1/4, minus this. So this is the vector 3/4 plus root 2 over 4 minus root 3 over 4. So this is a vector, oops, this is minus 3 over 4 plus root 2 over 4 minus root 3 over 4. So this vector is a unit vector pointing in the direction opposite to that of v. And I want a vector of length 5 in this direction. So the vector that I'm looking for, the answer is going to be 5 times the vector minus 3/4 root 2 over 4 minus root 3 over 4. So that's minus minus 15 over 4, 5 root 2 over 4, minus 5 root 3 over 4. And I don't know why I keep writing these square roots where they don't belong. But this is 10. So the answer is minus 15 over 4. 2 over 4 is a half times 5. 5 halves minus 5 root 3 over 4. So this vector should have length 5. Let's just check the length. So the length of this vector is the square root plus minus 15 over 5 squared plus 5/2 squared plus minus 5 root 3 over 4 squared. So if I square all that, I get 225 over 16 plus 25 over 4 plus 75 over 16. 25 over 4 is the same as 100 over 16. So if I add this up, I will certainly get the wrong answer. So I have to figure out what I did was wrong. But that's good. I'm always happy when I make mistakes like that. Let me just go back and double check everything. And as I'm going through these things, if you see that I've made a mistake, you should certainly interrupt and tell me. So I start with the vector 3 minus 2 root 3. So the length of this vector, 9 plus 4 plus 3 is 16, and the square root is 4. So this vector has length 4. So if I divide this vector by 4, I get a unit vector in the direction of v. And if I multiply this vector by minus a fourth, I get a unit vector in the direction opposite to v. So when I scalar multiply this vector by minus a fourth, I get minus 3/4 plus a half. 2 over 4 is a half. Sorry, I get minus 1/4. No, I'm sorry. Let me just. Here, I didn't want that. Minus 3/4 plus a half. 2 over 4. I could have just written that as a half. Minus root 3 over 4. So this is a unit vector in the direction of v. But again, something here doesn't look right. Minus 3 over 4 plus a half minus root 3 over 4. Yeah, no, that's right. Minus 3 over 4 half minus root 3 over 4. So this is a unit vector pointing in the direction opposite to v. And I want a vector in that direction of length 5, so I multiply by 5. When I multiply by 5, I get minus 15 over 4, 5/2 minus 5 root 3 over 4. So if I do my arithmetic correctly, this should be a vector of length 5. So what is the length of the vector? You take the square root of the sum of the squares of the coordinates. So I get 225 over 16 plus 25 over 4, which is the same as 100 over 16, plus 75 over 4. So this is the square root of 400 over 16, which is the square root of 25, which is 5. So it does check. I thought I had made a mistake, but I didn't. That's lucky. Okay. So that's problem 69. And spend a minute, just look at this, or hopefully you're not watching this lecture without sort of pen and pencil or paper and pen or paper and pencil handy. And just go through and check these calculations and make sure you can do it and you get the right answer. There are different ways to do the problem, but there's only one answer. No matter how you do the problem, the correct answer is always this. So that's what you should get.
Professor,
Yeah.
before you get to square root of 25, is that 400 over 10 or what?
Sorry. What are you asking about?
The last to the answer, is this 400 over 10 or what? This one.
Where
No,
my pencil is?
where you get to the answer, square root of 5.
There's no
Where
square
you
root
get-
of 5. I have square root of 25.
This is 400 over 10.
No, this is 16. This is denominator 16. 400 over 16.
Okay, thank you.
Wait, Professor, what's the second one that it says, that you cross it out where it says 225 over 16 plus? Is that 100 over 16 or
Oh,
what?
so what I had, when I square 5 halves, that's 25 over 4,
Yeah.
but I want a common denominator of 16, so that's 100 over 16.
Okay, got it.
So that's all.
Okay.
Okay. Let's maybe look at one more problem that could be interesting. So let's look at a problem in geometry. Then we might be able to think about using vectors. So this is exercise number 83. So you have a triangle. And in the plane, in 3 space, here's the origin, the 0 vector. And this is U, and this is V, and this side is W. So this is problem 83. Assume U, V, and W are vectors in R3, in the plane, in space rather, that form the sides of a triangle. Use the following steps to prove that the medians intersect at a point. What's the median? What are the medians of a triangle? You take a side, find the midpoint, and draw the line from the opposite vertex to the midpoint. That's one median. But of course, a triangle has 3 sides. So there are 3 medians. If I find the midpoint of U, here is the midpoint to this side. And if I find the midpoint of W, this is the midpoint to W. Now, it's a theorem in geometry that if you draw the 3 midpoints, they intersect at a point. I mean, it could be you had a picture like this. This was one median, this was one median, and this was another median, and they don't intersect at a point. But in fact, if I draw the pictures correctly, carefully, you see that the medians always do intersect at a point. And not only that, but each median is divided in the ratio of 1 to 2. So this and this and this, these are all the same lengths. So if you look at the median and you find the point of intersection of the 3 medians on that given median, one of the halves of that line is exactly twice that of the other half. So if we call this U, and this V, this W. So if you take U plus V plus W, again, these are not lines, these are vectors. So U is the vector from 0 to this point. V is the vector from the head of U over to here. W is the vector from the head of V back to the origin. And U plus V plus W is 0. If you just do your vector addition, U plus V is here. U plus V plus W, you're back here. So the sum of these three vectors is always the 0 vector. Then I want to let M1 be the vector from the midpoint of U to the opposite vertex. So this is M1. And M1 is going from the midpoint of U to the opposite vertex. And M2 is going to go from the midpoint of V to the opposite vertex. And M3 will go from the midpoint of W to the opposite vertex. And we want to show that M1, that vector, is half of U plus V. But here's M1. U over 2 is here. So if you look at this from the point of view of vector addition, from here to here, that's U over 2. And then if I add M1, I get over here. And that is the same as U plus V. So M1 is U over 2 plus V. That's what this equation says. And if we wanted to try to find similar expressions for M2 and M3, let's put this down so it's visible. Here is M2. So if I were to take U plus V over 2 plus M2, I get back to the origin. Right? If I go U plus a half V plus M2, that's 0. So this says that M2 is equal to minus U minus a half b. And M3, if I were to go from here to here, which is minus W over 2, plus M3, that would be U. So M3 would be equal to U plus a half W. So I have three equations that look like this. And then if I let this vector be A and this vector be B and this vector be C, what does that say? No, sorry. From 0 no. This is going to take a little bit too much time. Maybe I'll do this in our next class. But what's very interesting, if you look at these problems at the end of the section, they're always rather interesting problems that use the material in the section in unexpected ways. So it's a very famous theorem in geometry that not only did the three medians of a triangle intersect at a point, but the point bisects, not bisects, cuts each of those medians in the ratios of 1 to 2. And what this exercise is showing, will show, is that you can use vectors to prove this. All right. Are there any questions before we end for today? If not, then I will see you all next week. Bye all.